All right, welcome back. Let's get straight into it. We have to bound some position vectors. Bound some position vectors. Bound some position vectors. Okay, so we want to find estimates like this. We're going to do it in two stages. The first stage is going to be bound, so we're going to do it in two steps. Step one is going to be to bound the L2 norm. And then the second step will be to use that to bound the L infinity norm, the supremum, or the essential supremum. Okay, I'm going to show you both steps. So first, we're going to calculate ddt. Now, this is not really a geometric quantity, which is why this is sort of awkward. This integral, so what are we doing here? Let me write down this integral. It's this integral, and it's not geometric because if you translate the origin, so if you just move the origin up or down or wherever you want, this quantity will change, and it can get arbitrarily large. So that's not good. Whereas we were talking before, the fundamental invariant in Euclidean geometry is curvature, and it's invariant under rigid motion. So for this problem, naturally invariants that respect rigid motion are good and clean and nice, and this integral is not one of them. So the position vector is actually not a geometric quantity, which is why controlling it's a bit weird, but we're fine. We're going to be totally fine. So we can calculate this. Okay, first the derivative hits the gamma squared, and we're going to get a 2. Okay, we're going to get 2 gamma t, which we can just substitute for directly. Don't worry about that. And then we're going to get the derivative landing on the arc length element, which is going to give us the term that we had before, which was, oh, 1 second. Sorry about that. What was it doing? So we differentiate this integral, and we first land on the gamma squared. We get this gamma t, which we can substitute for, and then we land on the ds, which we know how it evolves. You remember, it's kf, and then if we're still carrying around this tangential term, we can stick it there. And the gamma t is minus f normal plus tangential term if we still have it, like this. Oh, and this is, why is there a 2 there? Guys, you've got to tell me when I make a mistake. This is a gamma. Alright. So let's just collect together the tangential terms, tangential velocity terms, because these should not make any difference. So we've got t gamma tau from the first term, and then from the second term we've got 1/2 gamma squared t s ds. Look at that, it's beautiful, never ceases to amaze me. So if you integrate by parts on this, the boundary term vanishes because t vanishes on the boundary, and you end up with exactly minus this, so they cancel each other out. I love that. Okay, and then what we've got for the first thing here, we've got minus integral f, and then this is gamma in the normal direction, and here we have 1/2 integral gamma squared k times f ds. Alright, and now we just do a very general estimate, because our f, our k, all these things just depend on k and kss, and that is all uniformly bounded by Chuk-Kuvert-Schätzler, and even the L infinity norms are all uniformly bounded because we can just use the Poincaré or Wirtinger inequalities in their L infinity form and to bound all those things. So everything here is bounded. The only thing that's not bounded is the gamma, yet. So we end up with a constant, universal constant, and we have two terms here, gamma and gamma squared. And now, in fact, so what we've got here on the left-hand side is d dt 1/2 gamma 2. And we can actually use a very simple estimate to remove this linear factor. Simple estimate is ab smaller than or equal to a squared over 2 plus b squared over 2. You know, just a simple little estimate. You can prove that as a exercise if you like, but probably you've seen this many times and you know how to do it already. So this, I use this on the first gamma term, and we're left with a constant times length, which is just another constant. Okay, so we use the same letter C to mean a constant that can change from equation to equation, but is in every case uniform in time. Plus, and then this is just the one of these again. Okay, and now you see what we've got. We've got a function of time whose derivative is bounded by a constant plus itself. Well, that implies that it grows at most exponentially. Well, how? By Gromel inequality. So again, look it up. It's a cool thing. If you haven't seen it before, it's super fundamental and really amazing, and very useful when you're studying ODEs or even PDE, like in this case. So we get that the L2 norm of the position vector can grow at most exponentially fast. Okay, that's the first step. And you'll note that this proof works for all kinds of different flows. Okay, so we've got this. Now, to go from this to the L infinity form, we just do some decomposition. So we've got our goal, which is the supremum of the position vector. And now we just break this down into its coordinate functions. So you can think of these as x and y coordinates. I just call it first coordinate, second coordinate, because, you know, as long as you're using, say, an orthonormal frame, it's all good. And so E1 and E2 are my frame vectors, and that's just the decomposition of gamma into its coordinates, no problem. And now these are unit length, so this is certainly no bigger than the L infinity norm of this function plus the L infinity norm of this function. Okay, and now I add and subtract. I do that old mathematician trick. I add and subtract the average of each of these. No problem. Add and subtract. Oh, by the way, this is a 1, not a prime. I'm not differentiating anything. And now I use, again, triangle inequality to just split these into 2, because this first one is going... Oh, this symbol with the line on the top means average, by the way. This first pair, I'm going to be able to estimate using the Poincare inequality. And the second thing, it's kind of funny to write it down because this is just a number. It's an integral, but it's not a function of... I mean, you're taking the supremum of a number. So this is funny to write down, but I'm going to fix it up in a second. And then I think I'll use the next line for this one. It's exactly the same happening for the second coordinate. I am going to differentiate this soon, as promised, because we're going to use the Poincare inequality. And, okay, so you'll notice there's no square here. There's no square up here. It's a 1. So I need to take a square root when I apply my Poincare inequality in L2, L infinity L2. And it's going to look like So the constant is 2, it's my son, 2L over pi. And now what is the derivative of this first one with respect to arc length? It's the component of the tangent vector, tau 1 squared ds, and then we can't forget to take our square root. And then it's exactly the same thing for this second one, except instead of the first component, it's the second component. Okay, so I'll use the power of technology to assist me, and I'll change this 1 into a 2. I hope I can change the size of this eraser. Aha, it does work. Yeah, fantastic. 2. Okay. So these are obviously bounded because these are just going to be multiples of length, and the length is bounded by our preservation of our total turning condition. And then we've got these two averages, and like I said before, these are just actually numbers. 1 over L integral over the curve, and this is just this function gamma 1, this coordinate function. And the second one is the same, but gamma 2. So I just write them in the same integral, like that. So these are these averages. So when we added and subtracted here, we're adding and subtracting a number. And that number is this integral, it's this average. Okay. So now let's keep going. I think I'll drag this onto the next page. Let's keep going. So like I was saying before, this first two terms are just, because the tau is a unit vector, so this is definitely less than 1, so this is just less than some constant. And now what do we do with these guys? Well, we can estimate, we can use another simple, well, simple, elementary, it doesn't mean it's simple, but it's elementary, estimate for numbers. If you have any two numbers, a plus b, then you can estimate them. You can't estimate them just by this norm, but you can if you put a square root 2. Okay, so we're going to use that estimate. And I'll just put a c here. Okay, we're going to use these as our a plus b's. And then, of course, the square root of this squared plus this squared is just the definition of gamma squared. And now if you look back here, you'll see that we have an estimate from step 1 exactly for this purpose. Put this here. So we can estimate this by this. So we get constant plus constant e to the constant t. And now let's recall what's on the left. On the left, it's gamma infinity. Oh, wait a second, I made a mistake. Who can see the mistake? Sorry, in my excitement, I made a mistake. So this is actually just the norm of gamma. It's not the norm of gamma squared, like that. And then to get to the norm of gamma squared, we have to use the Hölder inequality with 1 and the length of gamma. And that's going to give us constant, depending on length, and the L2 norm to the power 1. Okay, and then so when we do the L2 norm to the power 2, you have to take a square root, and so we'll have to divide this exponent by 2, but of course that's just going to give us a different constant, and we don't care, so like that. Awesome. This is for both the curved diffusion flow and the free elastic flow. So this gives you a constant. Now if t is smaller than capital T, then this is a finite number, and the local well-posedness result can just continue to apply again and again and again to give us our global existence. So I'm going to say that t equals infinity, follows. Okay, that's the end of what I wanted to do for today. Next time, we are going to move on to the next section and talk about how we show that the curve actually gets closer and closer and as close as we like to a straight line. Okay, I'll see you then. Thank you for your attention. Take care of yourselves. Peace.